They didn't just build machines, they built America. In the mountains of West Virginia, on the slopes of the Sierra Nevada, deep inside the pine forests of Michigan and the coal hollows of Appalachia, there were men, ordinary men with calloused hands and ruined backs, and lungs full of smoke. Men who woke before dawn, ate in silence, and walked out into a world that wanted to kill them. And the machines they ran, those iron giants, those machines shaped every city, every industry, every road, every building that came after them. Without these engines, America as you know it does not exist. But here's the thing. Nobody talks about them anymore. You know the big boy. You've seen the streamlined passenger locomotives. You've heard of the transcontinental railroad. But the machines I'm going to tell you about today lived and died in places that never made the newspapers. They hauled timber out of mountains that had never felt the weight of a human foot. They dragged coal through tunnels so full of smoke that men choked and prayed. They climbed grades that should have been impossible. They built the infrastructure of an entire civilization, and then they were scrapped, or forgotten, or left to rust in a field somewhere. This is the story of 5 forgotten steam engines that built industrial America. Not the glamorous ones, not the record breakers, the ones that did the real work, the brutal work, the work that cost men their lives and cost the land itself something it has never fully recovered. I've drawn from 2 extraordinary chapters of American industrial history for this story. The world of the logging railroads, those astonishing temporary rail lines that carved 50 miles of track into the wilderness just to tear it all up 5 years later. And the forgotten steam giants, the experimental behemoths, and the engineering nightmares that pushed the boundaries of iron and fire until something broke. Together they tell a story about what it really cost to build industrial America. So let's go back, all the way back, to a time when the forests were endless, the mountains were untamed, and the machines that would tame them were just beginning to be born. The year is 1878. The forests of Michigan's Upper Peninsula stretch from horizon to horizon, a cathedral of white pine so dense and so ancient that the light never reaches the ground. And somewhere in that forest, a man named Shay is having a very bad day. Shay is a logger. He runs a small timber operation on the banks of the Elk River, and he's been watching conventional locomotives fail on his logging lines for years. The problem is simple and brutal. Standard locomotives are designed for flat, smooth track. They have large driving wheels optimized for speed, and they need a firm, well-graded roadbed to generate traction. The logging industry doesn't have flat ground. It doesn't have a smooth track. It has mountains and mud and grades so steep that a conventional locomotive would just sit there, wheels spinning, going nowhere. Shay is a practical man. He doesn't commission a study. He doesn't write a report. He builds something. What he builds is unlike anything that has ever run on rails. The conventional locomotive of the era used large driving wheels connected directly to steam cylinders, a design that worked beautifully on mainline track, but failed completely on the rough, steep, inadequate track of a logging operation. Shay's solution was elegant in its logic and radical in its execution. He geared down the power. Instead of connecting cylinders directly to driving wheels, Shay mounted a vertical steam engine on one side of the locomotive frame and connected it to a horizontal crankshaft that ran the full length of the machine. That crankshaft connected through bevel gears to the axle of every single wheel on the locomotive. Every wheel, all of them turning together in mechanical solidarity. The result was a locomotive where brute force replaced elegance. A Shay couldn't run fast. Top speed was maybe 15 miles an hour, and most operations ran them much slower than that. But Shay could climb. It could haul heavy loads up 10% grades that would have sent a conventional engine sliding backward, wheels spinning uselessly on rain-slicked rails. It could do this on rough track, on poorly maintained track, on track laid down in a week by men with picks and shovels. It could do it in rain, in mud, in the kind of terrain that killed horses. Ephraim Shay patented his design in 1881 and licensed it to the Lima Machine Works in Ohio. Lima would eventually build over 2,770 Shay locomotives. They went everywhere the timber was, to the redwood forests of California, to the spruce forests of Oregon, to the coal hollows of West Virginia, to the pine barrens of the Deep South. Wherever a man needed to get heavy loads up impossible grades, a Shay was waiting. But here's what I want you to understand about the Shay. It wasn't just a machine, it was a philosophy made of iron. The logging railroads that ran these engines were not permanent infrastructure. They were not built to last. They were built to extract. A logging company would survey a stand of old-growth timber, maybe 10,000 acres of Douglas fir in the Cascades, trees that had been growing since before Columbus, and they would calculate its worth. At 1900 prices, a single mature Douglas fir could yield 20,000 board feet of lumber. One tree, that tree was worth $400 to $600. In today's money, $15,000 to $20,000 per tree. Now imagine 10,000 of those trees. You're looking at millions of dollars standing on a mountainside, and the only question is how to get it out. The answer was Shay, and the temporary railroad it ran on. A logging company would spend $300,000 building 50 miles of track into the wilderness. They would blast tunnels through granite. They would span mountain gorges on wooden trestles built from green timber, cut right there on the job site. They would grade the roadbed by hand, with picks and shovels and wheelbarrows, an army of men moving through the forest like something between a construction crew and an invading force, and the Shay would crawl up that track, car by car, log by log, pulling the timber out of the mountains. The men who ran these locomotives learned skills that had no name in any engineering textbook. They felt the track through the throttle. They sensed when a rail was about to spread under the weight of a loaded car, or when the roadbed was softening beneath them after a night of rain. They worked brake valves with a delicacy that seems impossible when you consider they were holding back 200 tons of timber on a grade so steep that the front of the locomotive seemed to point at the sky. And when the timber was gone, when the last tree on that 50-mile stretch had been cut and loaded and hauled to the mill, they did something extraordinary. They tore up the railroad, every rail, every spike, every tie. They loaded it onto flat cars and moved it to the next forest and built the whole thing again. The Shay locomotive was the tool that made this possible. It was the machine that unlocked the American forests, that turned standing timber into the lumber that built the cities of the West. And when those forests were gone, the Shay went with them, into museums, into tourist operations, into the slowly dimming memory of the men who ran them. Picture what it actually looked like to run a Shay on a logging grade in the Pacific Northwest in 1905. You're in the cab before sunrise. The air smells of pine sap and coal smoke and the particular cold dampness that comes off a West Coast mountain morning. Your fireman is already working the stoker, feeding the firebox, watching the pressure gauge climb. Outside the cab windows, the forest is a wall of black. The trees so tall and so close to the track that their branches brush the sides of the locomotive as you move. The grade begins. You feel it before you see it, the locomotive leaning back slightly as the track tilts upward, the exhaust note deepening from a quick chatter into something slower, more deliberate, more labored. You ease the throttle forward, the gears engage. You feel, through your hands on the throttle bar and through the soles of your boots on the deck, the mechanical heartbeat of the Shay, that distinctive rhythmic chuffing that old-timers said sounded like nothing else on earth, and that you could hear, on a still morning, 2 miles away across a mountain valley. The trestle comes up fast, 180 feet of green timber spanning a ravine, built 3 weeks ago by men with axes and a lot of confidence. You've crossed it a dozen times and it still makes your stomach tighten. The whole structure sways under the weight of the locomotive. You can hear the timbers groan. You don't look down at the creek far below. You look at the track ahead of you, and you breathe, and you trust the wood, and the math, and the men who built it. This was the daily reality of Shay locomotive operations. Not glory, not adventure. Work. And yet, and this is the thing that gets lost in the museum plaques and the tourist railroad brochures, these men were extraordinarily skilled. The ability to feel a locomotive through your hands, to read a grade through the sound of the exhaust, to hold 200 tons of timber on a mountain descent using nothing but the geared braking of the engine and the careful application of the brake valve, that is a skill that took years to develop and that once the logging railroads closed, vanished from the world entirely. Today, a handful survive. The Roaring Camp Railroad in California runs restored shays through second-growth redwoods. The Cass Scenic Railroad in West Virginia operates them on original logging grades, climbing into mountains where the timber was cut more than a century ago. But the men who ran them in their prime are all gone. Their knowledge and their stories went with them. What remains is the landscape itself. The old grades cut into the mountainsides, the rotted stumps of trestle bents, the rusted spikes that turn up in the forest floor 100 years later. Monuments to a machine that changed everything. You've heard of Shay. But Shay didn't work alone. In the hills of Pennsylvania in 1888, a man named Charles Scott was running a logging operation and watching Shay locomotives do their work. He thought he could do better. The Shay was mechanically complex, that longitudinal crankshaft, those bevel gears, that offset boiler. And complexity meant maintenance. In a remote logging camp 50 miles from the nearest machine shop, a broken Shay meant a broken operation. Scott's solution was the Climax locomotive. Where the Shay used a vertical engine driving through a longitudinal crankshaft, the Climax used angled cylinders set at roughly 30 degrees from horizontal, driving a central gearbox that transmitted power to both trucks. The design was mechanically simpler than the Shay, with fewer moving parts and a more conventional boiler arrangement. It was easier to maintain. A camp mechanic who had never seen a Shay in his life could figure out a Climax. It sacrificed some of the Shay's legendary hill-climbing ability. On the steepest grades, in the most desperate terrain, a Shay would outlast a Climax every time. But for logging operations on terrain that was merely brutal, rather than absolutely insane, the Climax was often the better choice. The Climax Manufacturing Company of Corry, Pennsylvania, built over 1,000 of these locomotives between 1888 and 1928. They hauled timber in the Appalachians, in the Great Lakes states, in the Pacific Northwest. They were workhorses in every sense of the word. Not beautiful, not famous, just endlessly capable. And then there was the Heisler. Charles Heisler was a Pennsylvania engineer who patented his design in 1892, and his locomotive split the difference between the Shay and the Climax in a way that made it uniquely suited to certain kinds of work. The Heisler used a V-twin engine, 2 cylinders arranged in a V configuration, mounted in the center of the frame. These cylinders drove a longitudinal shaft similar to the Shay's, but with a different gear arrangement that gave the Heisler a smoother power delivery. Heislers were popular in the Pennsylvania coal regions, where the track might be marginally better than a logging railroad, but the grades were still severe. They were prized for their ability to run in either direction without the awkwardness of the Shay's offset boiler, a practical advantage that meant a lot when you were constantly reversing on switchbacks. What I want you to understand about the Climax and the Heisler is that they were part of an ecosystem. The Shay got the headlines, the Shay got the patent, the Shay got the museum displays. But the Climax and the Heisler were there too, working the same impossible terrain, doing the same brutal work, running on the same temporary track that would be torn up and moved when the timber was gone. And the men who ran them, the engineers, the firemen, the brakemen, didn't care which manufacturer's name was on the cab. They cared whether the machine would hold together long enough to get the load down the mountain. They cared whether the brake would hold on that particular grade after a night of rain had made the rails slick as ice. They cared whether the trestle they were about to cross had been inspected that morning or whether the foreman had simply waved them on because the timber wasn't going to haul itself. The logging camps that supported these operations were places of extraordinary physical deprivation. A typical camp housed 50 to 200 men in bunkhouses that smelled of sweat and tobacco and drying wool. The bunks were built 3 high. You slept on a mattress stuffed with straw or fir boughs. The dining hall served enormous meals, 4,000 or 5,000 calories a day, because the work burned everything you could eat and demanded more. There was no privacy, no quiet, no comfort. When the trees within reach of the current line were cut, the entire camp moved. The bunkhouses came apart into sections that could be loaded onto flat cars. The dining hall was built the same way. The crew would go to sleep in one clearing and wake up in another, the same bunkhouse in a different location, surrounded by a different section of forest that looked exactly the same until it too was cut. This was the world the Climax and the Heisler inhabited. Not glamour, not history, just work, and more work, and the slow grinding depletion of men and forests alike. Together, these 3 geared locomotive designs, the Shay, the Climax, and the Heisler, were the tools that opened the American wilderness. They were what made the logging railroad possible. And the logging railroad was what made the great timber harvest possible. And the great timber harvest was what built the cities. Think about that for a moment. Every wooden building in San Francisco, every lumber yard in Seattle, every timber frame house that went up as America expanded west in the early 20th century. That wood came out of mountains on the backs of geared locomotives, hauled by men who risked their lives every day for wages that would seem insultingly small by modern standards. The last commercial geared locomotive operations shut down in the 1960s. The men who ran them are gone. The forests they harvested are gone. Or rather, what remains is a pale shadow, second-growth timber that will never match what came before. But the machines themselves, a handful of them, survive. They run on tourist lines, carrying passengers who have no idea what these engines were built for, no idea what they cost, no idea what happened on those mountain grades a century ago. That's a history worth knowing. Now we leave the forests and enter a different world, the world of the mainline railroad, where the money was bigger and the engineering ambitions were bigger, and the failures were correspondingly spectacular. The year is 1914. The Erie Railroad is struggling with a problem that's familiar to anyone who's ever tried to move heavy freight over mountains. The grades on the Erie's main line were severe, and the coal and freight trains of the era required multiple helper locomotives just to get over the summits. Helper locomotives meant extra crews, extra maintenance, extra expense. The railroad wanted a single locomotive powerful enough to replace 3 or 4 helpers. They went to the Baldwin Locomotive Works, and they asked for something that had never been built before. What Baldwin delivered was the Class P1, a 28882 Triplex. Let me explain what that means. A conventional locomotive had 1 set of driving wheels. A mallet-articulated locomotive had 2 sets, an arrangement that was already considered exotic and powerful. The Triplex had 3 complete sets of driving wheels, 3 separate steam engines, sharing a single boiler, generating a tractive effort of over 160,000 pounds. For comparison, a standard freight locomotive of the era generated maybe 40,000 to 50,000 pounds. The Triplex generated more pulling force than anything that had rolled on rails up to that point. The locomotive was named the Matt H. Shay after a beloved Erie Railroad employee, and it weighed over 850,000 pounds. It was almost physically staggering. The 3rd set of driving wheels was mounted beneath the tender itself, using the weight of the coal and water to add traction. Baldwin promised the Erie that this machine could haul 640 loaded freight cars in a train stretching nearly 5 miles. 5 miles of freight, pulled by a single locomotive. That was the dream. The reality was one of the most complete engineering failures in American railroad history. The problem was the boiler. A single boiler, however large, cannot generate enough steam to feed 6 hungry cylinders simultaneously. Push the triplex past 10 miles an hour, and the steam pressure collapses. The locomotive would slow, labor, and eventually stall. Not because it lacked pulling force, but because it was starving for steam. There was another problem, more subtle but equally crippling. Only the front set of cylinders exhausted through the smokestack, creating the draft that pulled air through the firebox and kept the fire burning hot. The rear cylinders exhausted through a separate stack on the tender. Those rear cylinders were essentially freeloaders. They consumed steam without contributing to the draft that made more steam possible. And as the tender consumed its coal and water on a long run, the rear driving wheels lost adhesion. The very weight that was supposed to give them traction was disappearing with every mile. The triplex was designed to get weaker as it worked harder. The drawbars and couplers of the era couldn't handle the forces the locomotive generated when it was working at full effort. The Erie relegated the Matt H. Shay and its two sisters to pusher duty on Susquehanna Hill near Deposit, New York. They were good pushers, each one replacing 3 conventional helper engines, but this was not what they were designed for. The Virginia Railway ordered its own triplex, classified XA and numbered 700, and that locomotive was even worse. It could barely manage 5 miles per hour before running dry on steam. Baldwin sent their own engineers to fix the problem. They couldn't. The Virginia Railway sent number 700 back to Baldwin in 1920, where it was dismantled and rebuilt into 2 separate, more conventional locomotives. Both of those conventional locomotives went on to serve reliably until 1953. By 1927, all 3 Erie triplexes had been retired. By 1933, every last one had been scrapped. Not a single triplex survives. What killed the triplex wasn't bad intentions. The engineers who designed it were brilliant men working with the best tools and knowledge available to them. What killed it was the fundamental thermodynamic limit of the steam boiler. The fact that there is only so much steam a given boiler can produce, and that limit cannot be overcome simply by adding more cylinders. The triplex is a monument to the dangers of promising more than physics will allow. But it's also something else. Evidence of how desperately American industry was pushing against the limits of steam technology in the early 20th century. The railroads needed more power, they needed to move more freight over higher grades at higher speeds, and they kept reaching for designs that might break through to something new. Consider what it must have been like to work on one of these machines when it was first delivered. The shop crews would have gathered around it the way workers gather around anything new and expensive and much anticipated, with a mixture of pride and skepticism. The official numbers were astounding. The theoretical tractive effort was higher than anything ever measured. The sheer physical presence of the machine, that enormous triple-jointed body stretching out across the track, would have been genuinely awe-inspiring. And then the first test run. The locomotive would have moved well enough at slow speed, hauling cars up the grade with a power that seemed to justify every optimistic claim. Then someone pushed it to 15 miles an hour, and then 20, and the steam pressure began to drop. Not dramatically, not at first, but steadily, inevitably, as the 6 hungry cylinders consumed more steam than one boiler, however large and however hot, could produce. The engineers on those test runs would have known something was wrong before anyone admitted it officially. They could feel it through the throttle. The power was fading. The machine was running out of breath. Baldwin sent their own engineers to ride along and diagnose the problem. They came back with reports. The railroad's engineers wrote their own reports. Everyone understood what was happening. Nobody had a solution because there was no solution. You cannot repeal thermodynamics with engineering ingenuity. The boiler could only do what a boiler of that size and that pressure could do. Most of those designs failed. A few succeeded. And the story of how American engineers learned to tell the difference is one of the great untold stories of industrial history. For every triplex that failed, there was an Allegheny that succeeded. And the Allegheny did not merely succeed, it transcended. The year is 1941. The Chesapeake and Ohio Railway has a problem that is both simple and immense. It needs to move coal. Specifically, it needs to move enormous quantities of coal from the coal fields of West Virginia over the Allegheny Mountains to the industrial markets of the East. The grade from just east of Roosevelt, West Virginia, to the summit at Allegheny, Virginia, is 13 miles at 0.57%, not the steepest grade in the world, but maintained over distance, with trains weighing 11,500 tons. It is utterly punishing. The C&O went to the Lima Locomotive Works in Ohio and asked for something that had never existed before. A locomotive capable of moving those trains at speeds that made economic sense. Not crawling, not struggling, moving. What Lima delivered in December 1941 was the H8 class, the locomotive the railroaders called the Allegheny, and it was, by any measurement that matters, the most powerful steam locomotive ever built. The numbers are staggering. 4 cylinders, each 22.5 inches in diameter, with a 33-inch stroke. Boiler pressure of 260 pounds per square inch. Peak output measured between 6,500 and 7,500 horsepower on the dynamometer car, a measurement that has never been surpassed by a reciprocating steam locomotive, before or since. Each Allegheny weighed roughly 771,000 pounds. The tender alone held 25,000 gallons of water and 25 tons of coal. A typical run on the C&O saw one H8 on the head end and another pushing from the rear, hauling those 11,500-ton coal trains over the mountains. They made that run in just under 2 hours, moving at 45 miles per hour on the level stretches and grinding down to 20 on the ruling grade. Twice as fast as the older locomotives they replaced. The men who ran the Alleghenies speak of them with a reverence that borders on religious. At full throttle, one of these locomotives consumed 7 to 8 tons of coal per hour. The automatic stoker, a mechanical device that fed coal into the firebox, was capable of delivering over 12 tons of coal per hour. The fireman's job was not to shovel coal. His job was to manage the most voracious furnace ever mounted on wheels, to keep the water level right and the pressure up, and the enormous beast fed and satisfied. At 260 pounds per square inch, the Allegheny's boiler was operating at pressures that would have seemed impossibly dangerous to an earlier generation of engineers. The walls of the boiler were thick steel, engineered to tolerances that would have astonished a blacksmith of 50 years before. But thick steel is not invulnerable, and the crown sheet, that critical plate at the top of the firebox, separated from the inferno below by nothing but a few inches of water, was always the point of maximum vulnerability. If the water level dropped too low, even briefly, the crown sheet would be exposed to direct flame. The C&O paid the engineer's widow $10,000 in compensation. $10,000 for a man's life, for a death that was preventable, for a failure that may have been known and ignored. Lima built 60 Alleghenies for the C&O in total. Despite being practically new, the oldest barely a decade old when the decision was made, every last one was retired by 1956 as diesel locomotives swept the railroad. The economics of diesel were simply too compelling. A diesel didn't need a fireman. It didn't need a water tender every 100 miles. It didn't need a specialized crew trained to manage the most powerful steam locomotive ever built. Today, only 2 Alleghenies survive. Number 1601 at the Henry Ford Museum in Dearborn, Michigan. Number 1604 at the Baltimore and Ohio Railroad Museum. The rest were scrapped. 60 locomotives, 2 survivors. That is the ratio at which industrial America discarded its past. Our final engine is different from all the others. The Shay conquered terrain through mechanical ingenuity. The Triplex failed through thermodynamic hubris. The Allegheny succeeded through sheer, almost incomprehensible power. But the Southern Pacific cab forward is something else. A machine that exists because men were dying, and someone finally did something about it. The story begins in 1908, In the Sierra Nevada, the Southern Pacific Railroad Sacramento Division crossed the Sierra Nevada through Donner Pass, one of the most challenging railroad routes in North America. The grades were severe, the tunnels were numerous, and the snow was relentless. For decades, the railroad had built timber snowsheds over long stretches of track to keep the line open through the brutal Sierra winters. By 1908, there were nearly 40 miles of these enclosed timber structures, essentially wooden tunnels covering the tracks through the worst of the mountain terrain. The railroad took delivery of two new 2882 Mallet compound locomotives from Baldwin in 1908, designated Class MC1, and numbered 4000 and 4001. These were conventional locomotives, powerful, modern, well designed by the standards of the day. The SP assigned them to the mountain grades, expecting them to transform operations over the Sierra. On the first test runs up Donner Pass, the crews discovered a terrifying reality. A large steam locomotive exhausts enormous quantities of smoke and steam from its stack. On open track, this dissipates harmlessly into the air. Inside a tunnel, or inside 40 miles of timber snowsheds that functioned as tunnels, it had nowhere to go. The exhaust filled the enclosed space and poured back through the cab windows. The men inside were breathing smoke and toxic gases. The stack exhaust velocity was so powerful it even blew the roof boards off the snowsheds. The crews were being asphyxiated by their own locomotives. This wasn't a minor inconvenience. It was a life-threatening emergency. The alternative was simple. Don't use the new locomotives on the mountain grades. But the mountain grades were exactly where the SP needed them most. Legend, and it is at least partly legend, though the core of it is probably true, has it that one resourceful engineer decided he'd had enough and simply turned his locomotive around. He ran it tender first through the tunnels, so the smokestack was behind him and the exhaust stayed in the rear. It worked after a fashion. The tender blocked his forward view, put him on the wrong side of the cab for reading signals, and tenders were never designed to be pushed at speed. But the men could breathe. Other crews followed suit, and Southern Pacific, faced with the reality that their crews were improvising solutions to a problem that could kill them, went back to Baldwin and asked for something that had never been built before. What they asked for was a locomotive designed to run backwards by design. In March of 1910, the first true cab-forward locomotives rolled out of the Baldwin Works. These were Class MC2 2882s, numbered 402 through 416, and they looked like nothing that had ever run on rails. The cab was mounted at the very front of the locomotive, ahead of the boiler. The engineer sat in the nose of the machine, with the boiler stretching out behind him and the tender at the far rear. The key to making this work was fuel. A coal-burning locomotive couldn't run cab forward because you can't pipe coal from a tender at the rear to a firebox in the middle of the machine. But oil can be piped anywhere. The SP was already converting its California operations to oil fuel, and Bunker C fuel oil could travel through a pipe the full length of the locomotive to the firebox. The result was a machine that solved the asphyxiation problem completely. With the cab at the front and the smokestack behind, the exhaust streamed away from the crew as the locomotive moved forward. In the tunnels and snowsheds of the Sierra Nevada, the men could breathe, they could see, they could do their jobs without fighting against the machine that was supposed to be helping them. Think about what it meant to sit in that cab at the front of the locomotive. You were perched at the absolute nose of a machine that weighed close to 500,000 pounds. The boiler, the firebox, the driving gear, all behind you, invisible, and ahead of you only the track and the mountain. When you entered a tunnel on the old conventional locomotives, you were driving into the dark with smoke flooding back through your cab windows and the walls closing in on all sides, barely able to see the signals that told you whether the track ahead was clear. In the cab forward, you entered that same tunnel differently. The smoke went behind you. The air ahead of you was clear. You could see the signals, you could see the track. You could do your job the way a professional deserved to do it, with information, with visibility, with the basic dignity of being able to breathe. The cab-forward layout gave engineers the best forward visibility of any steam locomotive ever built. A massive safety improvement in the tunnels and around the mountain curves where visibility mattered most. And on those curves, the view from the front of the locomotive rather than the middle of it gave engineers crucial extra seconds to react to obstacles on the track. Southern Pacific ultimately rostered 256 cab-forward locomotives across multiple classes, making them the largest fleet of articulated mallet-type locomotives in the world. The final Class AC-12 models were delivered during World War II, with the last locomotive, number 4294, entering service on March 19, 1944. But even the cab-forwards weren't immune to tragedy. The oil line routing that made the design possible also created a unique hazard. Any oil leak ahead of the driving wheels could cause those wheels to slip on oil-slicked rails, and a slipping locomotive on a mountain grade is a runaway waiting to happen. On November 19, 1941, AC-8 class number 4193 entered the tunnel at Santa Susana Pass near Los Angeles with leaking oil lines. The tunnel sat on a grade, and as the train ascended, oil on the rails caused the wheels to spin. The train slid backward. A coupler knuckle broke. The airline separated, and the emergency brakes locked the train inside the tunnel, which was rapidly filling with exhaust. And then the oil dripping from the lines onto the wooden ties beneath the cab ignited. The resulting fire killed the crew. It was a reminder that engineering never solves problems completely. It only trades one set of problems for another. The cab-forward was created to prevent crews from being asphyxiated, and 30 years later, it still had the power to kill. The last cab-forward ran in September 1958. Today, only one survives, number 4294, the very last ever built, preserved at the California State Railroad Museum in Sacramento. The locomotive that was born from desperation, from the sight of men choking in smoke-filled tunnels, runs no more. But it stands in Sacramento as evidence that sometimes, just sometimes, the people in charge of machines listen to the people who run them. Let me take a moment to step back from the machines and think about what these 5 engines, the Shay, the Climax and Heisler, the Triplex, the Allegheny, and the cab-forward, actually represent. They weren't just locomotives. They were tools of a transformation so profound that we can barely see its edges from where we stand. The geared locomotives, the Shay, the Climax, the Heisler, opened the forests of America. The logging railroads they ran consumed old-growth timber that had been growing since the time of the Roman Empire, trees that were alive when Columbus sailed, forests that had evolved over thousands of years. In the space of a few decades, those forests were gone, not thinned, gone, and from that timber came the cities, the wooden frames of 1,000,000 houses, the wharves and bridges and warehouses, the furniture and the floors and the doors, the infrastructure of American expansion from the Mississippi to the Pacific coast. It came out of those mountains on the backs of geared locomotives, one log at a time. The men who ran those locomotives did not get rich from the timber they hauled. They were paid by the day or by the piece, and when the timber was gone and the railroad shut down, they moved on. The wealth they created went to the timber barons, to the company shareholders, to the men who owned the machines and the land and the timber rights. The loggers and the railroaders got calluses and broken backs and, too often, early graves. The accident reports from logging railroad operations make for grim reading. A brakeman crushed between cars when a coupling failed. A fireman scalded to death when a boiler let go on a steep grade. An entire crew killed when a trestle collapsed under their locomotive. A young man, 19 years old, killed on his 3rd day of work when a log rolled off a car and caught him against a rock. These men were recorded in ledger books and forgotten. The companies moved on because the timber wasn't going to cut itself. The mainline giants, the Triplex, the Allegheny, the cab-forward, worked in a somewhat less anonymous world, but the pattern was the same. When the Allegheny's boiler exploded at Hinton and killed 3 men, the C&O paid the widow $10,000 and moved on. When the cab forward killed its crew in the Santa Susana Tunnel, the railroad recorded the incident and continued operations. This is the part of the story that never makes it into the museum plaques. We romanticize the machines, the locomotives and the trestles and the daring engineers. But we forget that these machines served an economic system designed to maximize the extraction of profit from both the land and the men who worked it. I don't say this to condemn the men who built and ran these locomotives. They were doing the work that was available to them, in the way that the economy of their time demanded. Many of them took genuine pride in their skills and their accomplishments, and that pride was justified. Running a Shay up a 15% grade with 200 tons of logs behind you required intelligence, courage, and physical endurance that would humble anyone who had never done that kind of work. But I think we owe them the honesty of acknowledging what the system cost them: the broken bodies and the early deaths, the families left behind when the operation moved on, the communities that flourished for a decade and then vanished entirely, leaving nothing but a name on an old map and some foundations in the brush. The logging railroads are gone now. The old grades are still there in the mountains, suspiciously level paths through steep terrain, the rotted stumps of trestle bents marching across meadows that were once ravines filled with timber, rusted spikes turning up in the soil a century later. If you walk one of those grades in the Pacific Northwest or the Appalachians, you're walking through an act of industrial archaeology. The grade beneath your feet was cut by hand, with picks and shovels, by men who were paid $2 a day. The forests they cut have grown back, after a fashion. Second-growth timber covers much of the logged-over land now. But it is not the same. The old-growth forests that the logging railroads harvested were ecosystems that had developed over centuries. What replaced them is younger, simpler, less diverse. The creeks run warmer. The soil erodes more easily. The wildlife that depended on the old forests has never fully returned. The mainline giants left a different kind of legacy. The engineering lessons learned from the Triplex about the thermodynamic limits of steam boilers influenced every locomotive that came after it. The power principles proved by the Allegheny pointed toward the upper limit of what steam could do, a limit that diesel would blow past with uncomfortable ease. The cab-forward configuration of the SP's fleet influenced later locomotive design and demonstrated that unconventional solutions could solve problems that conventional thinking had declared insoluble. And then, very quickly, it was over. The diesel locomotive arrived, and the steam age ended not with a dramatic final stand, but with a series of quiet, economically rational decisions. A diesel doesn't need water stops every 100 miles. It doesn't need a fireman. It doesn't need a specialized maintenance crew who know how to manage a steam plant. It costs less to run. It is more reliable. It starts more quickly and stops more easily. By the late 1950s, the steam locomotives were being retired faster than anyone had expected. Machines that were barely a decade old went to the scrapper's torch. The economic logic was inescapable, even if it meant destroying locomotives that had cost millions to build and that represented decades of accumulated engineering knowledge. The men who had run them retired and died, taking their knowledge with them. The shops that had maintained them closed. The skills that had kept them running. The ability to feel a failing boiler through the pressure gauge, to hear the difference between a healthy exhaust note and one that signaled trouble. To manage a 200-ton train on a 14% grade with nothing but your hands and your experience, those skills vanished from the world. If you've stayed with me this far, I want to leave you with something to think about. We live in a world built by machines. The roads and bridges and buildings that surround you, the cities that house us, the infrastructure that moves our goods and our energy, all of it is downstream from the Industrial Revolution that these 5 engines were part of. The Shay's logs became the framing of houses that still stand today. The Allegheny's coal powered the steel mills that made the girders that hold up bridges you drive across. The cab forward's route through the Sierra Nevada still carries freight and passengers through those same mountains. The machines are gone, most of them, But their work remains, embedded in the landscape and the built environment, invisible and fundamental. The men who ran them are gone too, all of them now. The last ones died decades ago. Their names were never famous. They didn't get biographies or statues. They got ledger entries and, if they were lucky, pension payments. We owe them something for that. Not uncritical admiration, not nostalgia that papers over the exploitation and the danger and the environmental destruction, but honest acknowledgement of what they accomplished and what it cost them. The forests they cut and the power they generated didn't only build America's cities, they built the economic foundation on which every subsequent generation has stood. These weren't men who had the luxury of choosing easier work. This was the work that was available. And they did it with a skill and a courage and a physical endurance that should humble any of us who have never laid track on a 60-degree slope or nursed a failing boiler up a mountain in the rain. The 5 forgotten engines I've told you about today are 5 windows into a world that is entirely gone. A world of muscle and steam and iron, of temporary railroads and permanent consequences, of machines that were marvels of engineering pressed into service by a system that cared far more about profit than about the men inside the cab. That story deserves to be told. Not sanitized, not romanticized, but honestly, with all the complexity and moral ambiguity that honest history demands. If you ever drive through the mountains of the Pacific Northwest, or hike through the hills of West Virginia, or visit the California State Railroad Museum and stand in front of that last cab forward, locomotive 4294, the very last of its kind, take a moment. The men who built those machines, who ran them, who died in them, they're the reason you can stand where you're standing. They're the reason the cities exist, the reason the industries exist, the reason the world you live in has the shape it has. They deserve to be remembered, all of them. If this story resonated with you, subscribe to the channel. Every week we explore the forgotten history of American industry, the machines, the men, and the true cost of progress.